Welcome back, everybody, to the same video, same class. We are going to do 11.6. 11.6 is Jackie's favorite, everybody's favorite subject. Word problems. Wait, but that's not how they call them. They sneak it in. They call them applications of exponents and logs, logarithmic equations. Application serves a purpose. There's not just math to make you crazy. This is the good stuff. Compound interest, first topic. We actually gave you the formula last week. We said A equaled P times 1 plus R over N to the NT. This is for R is the interest rate as decimal. N is the times per year to compound. T is the number of years. P is starting principal. And A is final amount. Then there's the continuously compounded. A equals PERT. And the letters are all the same. R means the same thing, T means the same thing, P means the same thing, A means the same thing. Jackie wants $1 million. She can lock in 12% interest for 20 years. With continuous compounding. How much should she invest to achieve her goals? Her goal. There's a way to get 12%, but it's not continuous. It's 1% a month. It's certain stocks, the dividend yield is 1%. So you could lock in a 1% growth per month or 12% per year. But with the example we did the other week, we saw big numbers, the continuously compounding, and the actual value doesn't change a lot the bigger that number gets. So what letters do we have here for our things up there?
We have A,
We have A. What is A?
$1 million.
Oh, that's Jackie's all in on this one. She's like, yeah, fuck yeah, I didn't want $1 million.
We
You
have
know,
a R,
that stupid movie with the. You know, where he's like, oh, I want 1 million bazillion trillion dollars, this by the Shackmakers.
Austin Powers?
Yeah, Austin Powers.
Don't get me started. I can't talk because I like talking like Austin Powers. I'm not gonna be in trouble when I do it in here. What's R?
12%,
We do it as a decimal, it's what?
point.
What's N?
It doesn't say.
Doesn't say, it's continuously compounded, which means we don't need N. We're gonna use this formula and there is no N. What's T?
1 years,
What's P?
not stated.
Unknown.
P is B. So we have $1 million equals PE to the 0.12 times 20. So that's 2.4 right there, right? So P is gonna be 1 million divided by E to the 2.4. That's the exact answer, but that means nothing to Jackie. So Jackie says, let me get out a calculator and figure out what that shit is. I'm gonna take the exponent of 2.4. And I'm gonna take $1 million and divide by it. I'll round up to 9.6 just because we want to make sure she gets that million. Ain't gonna be nothing madder than fucking having $999,999 and fucking 98 cents. Cause of fucking rounding.
So, and you would take the natural log of both sides of that fraction.
We actually don't need the natural log.
Oh, because it's E itself.
The variable is not in the exponent here. That was tricky, wasn't it? Now, we can put a twist on this. Let's put a twist on this. Jackie only has 50,000. Her husband mysteriously died and left life insurance. Mysteriously.
She unlocked one of his shop rooms.
How long must she invest to get the million?
So.
Yeah. So we don't need the N again. Our R is still the same. Our A is still the same. T is now the unknown and P is 50,000. So we need to isolate the exponent. Divided by 50K. And what is that, 20 on the left side? If I take the natural log of both sides. Ln of e cancels, the exponent comes down. And I have just 0.12 t. So t is natural log of 20 divided by 0.12. But that don't mean shit to her either. She said, I want to know how many goddamn years. Tell me something fucking useful, Mr. Jones.
But I don't.
So about 25 years.
5 years where you pay 50,000 per year.
No, you invested 50,000 once.
So instead of getting $1 million in 12 years, I'd get $1 million.
No, 20 years to 25 years.
20.
And she started with about half the value. Because those extra 5 years are 5 years that she's at a higher principal, basically. It's like restarting and after 20 years. If I had started done this with 50,000, done 20 years, she would have had a certain amount after 20 years. And starting from there and going 5 more years to go on million. All right.
And just like how 401ks work and stuff like that or something.
I couldn't answer that. I'm not a financial specialist.
I think it's
If they invest through a bank
Because,
and
like,
does
you're
that,
under
yes.
Your retirement thing, you're supposed to like,
I think it's how IRAs work. But yeah,
One of them does like you invested in a certificate of deposit, still like that. And it's, yeah. You're doing shit like
but
this.
all of them rely on you making money on the stock market, so. it's not lots. So what-
Richter scale.
They do.
What's the Richter scale represent? Earthquake magnitude. The magnitude equals the log of I over IO. Where, what?
EIO.
IO is a constant. And I is the intensity at 100 kilometers. Like a seismograph 100 kilometers from the epicenter. What does it represent? I believe this is in centimeters. I don't know what IO is right now, so we're gonna do a problem that compares two earthquakes. In 1923, Tokyo had a magnitude of 8.3 earthquake. In 1995, Kobe in Japan had a magnitude of 7.3. How do these compare? So I'm gonna write two equations for this. I'm gonna say the magnitude in Tokyo. I'll give it T is 8.3. And that equals the log of the intensity in Tokyo over IO. And the magnitude in Kobe was 7.3. And we'll call that log of intensity of K for Kobe over IO. And this is log IT minus log IO. And this is log IK minus log IO. And these two are the same. So I'm gonna have 8.3, I'm gonna. I'm gonna subtract the second equation. Because if I do, the log IOs will cancel. And I get 1.0 equals log of IT minus log of IK. And I can put that together. This is log of IT over IK. There's not one like this on your test, don't worry.
We got it.
Sounds like it should be.
Well, I could have done one like this for Los Angeles. This is log base what?
10.
10. So we're gonna treat both sides as exponents for 10. And I get 10 equals IT over IK. So if I clear fractions, IT equals 10 IK. Tokyo's quake was 10 times stronger. Despite only being one apart. If they're two apart on the Richter scale, it's 100 times stronger. 3 apart on the Richter scale is 1,000 times stronger. They're exponents of 10. We're doing Richter scale in the log base 10. So like seeing small differences in the Richter scale seems small, but like 10 times the amount of fucking force was released. Destructive energy. I'm gonna just talk about some of the other examples before we get to the final one that we're gonna do. pH model. The pH of like a liquid. pH equals the negative log of H plus, where H plus is the hydrogen ion concentration of of something and concentration. And I wanna say that is moles per liter. So, those of you taking chemistry. That's where the pH system comes from. It's a math measurement, how that. Should surprise you, their numbers, right? A lot of things that travel in waves do this. Earthquake is a wave. It emanates from the center. Something that else travels in waves is sound. So sound waves or loudness. Often called sound intensity. And has a similar setup to the magnitude for the Richter one. L, which is loudness, is the log. Nope, it's 10 times the log. I over IO, where I is the intensity in watts per meter squared. And IO is 10 to the negative 12. A small number. So there's examples of like these two that you could see in the textbook if you want to see them. Another good one is Newton's law of cooling. Newton just didn't do just physics, he was an all-around badass. So if something's hotter than its environment, it's gonna cool, right? That's why you go stand in a fucking icebox, refrigerated room if you're really fucking hot. You go to the icebox if you work at a restaurant, fucking cool off pretty quick. Cause the ambient temperature around you helps you cool you. There's an equation that models it. T equals TS plus T naught e to the negative KT. That one is temp at time T. That's surrounding temp. T naught is initial temp. Or at T equals 0. That's usually what initial means. And K is a constant. And it's usually dependent on the material that's you're talking about. If you got a rod of iron that's hot and you're trying to cool it, that's different than, you know, a fucking tube of water. The constants are different. But exponents in this bad boy. There's examples of that in book 2. The one we're actually going to work through is the exponential growth and decay models. Y equals C e to the KT. C is starting amount. This just looks exactly like the continuously compounded formula with different letters. And I think they use different letters just to make sure it's like people don't mix it up. Y is ending amount.
This is for radioactive decay or
Radioactive decay is one way, population growth is another. We'll do a radioactive decay and we'll do a population growth one. K is greater than 0 for growth. Like population models. And K is less than 0 for decay. Like half-life. Radioactive models. And T is in years. So you hear like, we did some carbon dating on so and so, we found this to be this many years old. This is what they're doing. They physically measure the amount of carbon that's left and how much carbon should be in it if it was someone that freshly died. And go, how much is lost? So let's give an example. We'll do it one each. Plutonium. Plutonium. We'll go with isotope 230. Has a half-life. 24,360 years. If you start with 10 grams. What remains after 10,000 years? I start off with C is 10 grams, right? I know time is 10,000 years. Y is actually my end goal. How much remains? K is not 24,360. So what's K? So we're gonna have to figure out K before we figure out Y. We do have the information that the half-life is 24,360 years. So I can set this up, Y equals CE to the KT. Let's just say C is 2. And so half of that would be 1. Half-life means half remains after that time period. I don't know what K is, but T is 24,360. So we divide by 2, we get 1/2 equals e to the 24,360 K. Take the natural log of both sides. So K equals 24,360. Nope, that's on bottom. Natural log of 0.5 or 1/2 over 24,360. I don't know what that is, but we can figure it out. There's a lot of decimal places here. I'm not gonna use this yet. I'm gonna go on to solve my actual equation, just leaving K in. And we'll substitute this K later. So the question we wanna solve is Y equals C, which was 10 grams. E to K, which we now have, times 10,000 years. So I'm gonna take that in, I'm gonna plug that in. I'll multiply my K by 10,000. There's a bunch of decimals here. I'm not gonna round, I'm just gonna use a calculator and use it, treat that as the exponent for E. There's more stuff. And when I'm done. Y equals 7.5235778. Let's just say approximately 7.5 grams. Half-life. Natural log of 1/2. Divided by the time. Doubling time. Would be natural log of 2. Your K should end up being positive. Let's look at a population model. I pulled these numbers from a website. In 2010, London had. That's not London, that's London. 8.044 million. People. In 2020. It has 9.304 million people. In 2030. What should we expect? If growth stays the same. It doesn't, it fluctuates every year. They had growth per year. It's kind of neat. Website showed the population every year and actually listen to the growth rate. But they did this shit. All right, so we know we've got Y equals CE to the KT. We don't know K. K is the growth rate. And we don't know the 2030 amount. But if we treat 2010 as the start. And 2020 as the stop. What's the T value? 10. There's 10 years difference between them. And we can treat this as a start and a stop. So I divide by 8,000, 8 million. I don't know what that is. I'm gonna leave it like that. I'm gonna turn it back down to the decimal zone. You need that. If I take the natural log of both sides. I get 10K equals natural log. This side. So K equals 1/10 of that, if we divide by 10 or multiply by 1/10. I got, that shouldn't say that, there you go. K is approximately 0.01455, or you could say about 1.455% growth. But that's not what we're looking for. In 2030, what will we have? We can pick either one of these as a start year. I'm gonna use 2020 just so time is 10. So if I use 2020 as a start. 2030 is the unknown value. Gives me T equals 10 years. So Y equals, my start is now 9.304. E to the 10K again. But now we have K. And if you work this out in a calculator, you will get 10.761 million. Approximately. So these growth and decay problems oftentimes are two-part problems. You gotta solve it twice. That's reality. We don't know growth rates and, you know, they had to do this with every single isotope there is for radioactive decay.
And is it birth rates or is it accounting for immigration? Okay.
Natural difference.
I think this is just population, so it's doing everything. Now, this is a generic model for population growth. There are limiting factors, like we can fucking grow so large that we don't have the space or the resources to feed you, so there's a more advanced model. But when you're nowhere near that, this is a good model. And that's my time with you guys. On Tuesday, I will go over the practice exam. I strongly recommend you don't go through it until you've done the homework. Get some practice doing some of that, all this shit. Then try it out before Tuesday. Whether it's Monday, whether it's Sunday, both. That way you know where you struggle, where you don't. We'll do the practice on Tuesday. Test will be on Thursday, starting, I'll be in here at 2, so if you want to start at 2, you can. And I think I'll stay till 6 on that day, but don't try to show up at 5 and think I'm gonna give you 2 hours. Godspeed. I'm at the Base Center on Saturday too.